Welcome everybody. So in this video, we are gonna see some more of these meta-theorems that we're seeing in the last few videos. They are a bit more technical, but they'll be extremely useful for us in our proof of completeness that is coming up in the next couple of weeks. So we're actually gonna use these quite a bit. Well, we're gonna use the other ones too. They also help us understand better this notion of formal proof. Okay, so let's get to them. So the first one is this one called the generalization of constants. It says that if you have a constant symbol C, so it's a symbol in our vocabulary tau, that does not show up in a set of formulas gamma. It doesn't show up at all in gamma, but it might show up in phi. And we have a variable y that doesn't show up in phi. Okay, so C does not show up in gamma, y does not show up in phi. Let's add here that y is also not free in gamma. Just to simplify the proof, it's not necessary for the theorem to be true, but let's just add it to simplify the proof a tiny bit. Okay. Then, if gamma proves phi, right? So if there is a formal deduction of phi from gamma, then there is a formal deduction of for every y phi where the constant C is being substituted by y from gamma. So recall that this means in the formula phi, replace each occurrence of C by y. Okay, so that's what that says. Let's see an example of something like that. Suppose, for instance, that gamma is the group axioms, and let's consider the vocabulary tau, which contains the usual identity, an operation, a binary operation for groups, and we're going to add an extra constant C. Let's just suppose for some reason that we are looking at groups with an extra constant C, which I don't know what they mean. So let's consider, for instance, the following sentence that you can prove from the group axioms. It says that for every x and for every z, if x star c equals z star c, then x equals z. Okay, so that's something it's cancellation. You can prove it using the group axiom. You can do a formal deduction. It's going to be a bit long, the formal deduction, and tedious, but it's doable. It's not super crazy, but it takes some work to figure it out. But yes, you can find a formal deduction of this from the group axioms. So what I notice here that so the constant C does not show up in the group axioms. So we are in here. The group axioms don't talk about this constant C, just a new one that we just came up with. And the variable y does not show up in phi. So we can apply the theorem. So the theorem is going to tell us that the gamma can show, and I'm going to put the new part on red, that for every y, we have that for every x and for every z. So notice, by the way, this one up here is phi. X star y equals z star y. And then, right, so we replace the c by the y's, right? So this one up here, this formula down here is phi, where c was replaced by y. Oh, sorry, that one on there. That's what the theorem tells you that you can do. So if you have a proof of the first one, and essentially what's going on is that this one mentions this constant C along the way, but C is not in our assumptions. Our assumptions don't say anything about C. So if you can prove something about a constant without any assumption at all about the constant, you should, if things work the way they should, you should be able to prove that for every y that's true, because you didn't use anything about the constants, so it should be true for every y. So that's if the formal proof system that you have works correctly. So essentially this theorem is somewhat saying that the formal system that we have works correctly in that sense. Okay, so and again, this just means, like in this example, replace the C by the Y. That's what it is. Okay, so let's prove this theorem. The proof goes as follows. So we know that phi is a formal deduction of phi from gamma. So let alpha 0, alpha k be a formal deduction of phi from gamma. All right, so in particular, we have that alpha k is the same as phi. And recall that a formal reduction means that each of these alpha 0 to alpha k is either an assumption, a logical axiom, or it can be deduced from the previous one using modus ponens. So we claim that for every alpha 0, if we take alpha 0 and replace c by y, and then take alpha 1 and replace c by 1, and then take alpha 2 and replace c by 1, and then take alpha k and replace c by y, we get a formal deduction. And notice that in this case, that alpha k where cy is essentially the same as phi c replaced by y, where c is replaced by y, right? Because alpha k is phi. So this will give us a formal deduction of phi c replacing c by y. And then we're going to use generalization to add the for all up front that we need, right? So, okay, so why is this? Well, the proof of this claim is by considering the separate cases depending on what each of these alpha i's is, right? So for each I less than k, less than or equal k, we have three cases. First, alpha I is a logical axiom. We claim that in general, in this case, if you have a formula, if psi is a logical axiom, so is psi when you replace c by y. And why is that? Well, let's look at the logical axioms. Here are the logical axioms. Let's look that in each of these cases we have the property that we just mentioned, that if you have one logical axiom and we replace a constant by a variable y, then we still get a logical axiom, assuming that y doesn't show up in the rest of the formula. And let's look at it. Well, if you have a tautology, if you replace some constant by other constants, you're not doing anything inside each sentential variable. So each like block that corresponds to the sentential variables of sentential logic. So it stays a tautology. If you have a constant, well, the constants are not being touched here when you replace by a variable. This is another variable, so nothing changes. This still should be true if in alpha you replace the constant by a variable, a new variable. The same is here. This is if you replace this constant by the variable inside here and here, then it will be replaced here and here. Fine. Here x doesn't occur free in alpha. So again, if you replace the variable constant by a variable here and another constant by a variable here, so long as you don't use the same variable, you're fine. And these two, yes, nothing here and nothing here. Also, you can replace the constant by a variable. So in all of these cases, if the previous one was axiom, then you just replace the constant by the variable, and you still have an axiom. So then this one is okay. Okay, so what's the other case? The other case is that alpha I is an assumption, is in gamma. Okay, but in that case, what happens? Well, then the constant c doesn't show up in gamma. So alpha I replacing c by y is the same as alpha I, because c doesn't show up in alpha I because it doesn't show up in gamma. So alpha I, which is the same as alpha y, is also an assumption. It's also in gamma because it's the same as alpha I, which belongs to gamma. Okay, so and then the last one, and then modus ponens that says that there are two previous lines, j and l, below I, such that together we get alpha I. So alpha j is of the form alpha l implies alpha I. So that means this one together with alpha l will give us alpha I. This one is somewhere there is alpha I, So below somewhere you have alpha L, and below you have somewhere alpha L implies alpha I. So together they get alpha I. Right? So suppose that's the case, well, in the alpha case, because that one we know is a deduction, so it has to be one of these cases. But in that case, what do we know? But then we have that alpha J substituting C for Y is of the form alpha L substituting C for Y imply alpha I substituting C for Y. So we still have an application of most exponents in the new rule. Okay, so this was a kind of a very simple. We just checked that if this is a deduction and it satisfies that every alpha I is one of these three forms, then the same is true when you replace every C by the Y. Okay, so then that's a deduction, and then what do we get from there? The gamma proves phi when you replace C by Y. And now since Y is not free, so then by generalization, which is something that we proved in the videos last week, this theorem up here that says that if gamma can prove phi and x is not a free variable in gamma, then it can prove for every x phi. Okay, and that was the same idea, kind of like, because x was not being used in gamma. So if you can prove something about x, you should prove that for every x that's true. We're just doing the difference between constants now. Then by generalization, we get that gamma proves for every y phi c y. Then by generalization, we get that gamma shows that for every y phi with c replaced by y, which is exactly what we want. So that's the proof. The proof, we got a deduction. We replace c by y in each of them. Y was a variable that didn't occur free anywhere, so everything was fine, and then we could add the for all y up front using generalization that we had proved before. Okay, so that generalization of constant is going to be very useful. There are a few corollaries of this that are going to be useful too. Here is the first corollary that is essentially more than a corollary, just a restatement. It's maybe too much to call it a corollary. So it says the following. So if you have a constant c that doesn't show up neither in theta nor in gamma, so theta now is a formula, sentence or formula, then if gamma proves theta where x is being replaced by c, then gamma shows for every x theta without many assumptions or any assumptions on x actually. So that's why it's a bit nicer than the other one. The proof of this is essentially, this is the same thing as before, essentially by taking, so you want theta, you just take phi to be theta where x is replaced by c, okay? So then from here we get that, but then phi where c is replaced by y is essentially theta by definition cx and then cx. And what is this? This is theta, you replace x by c, and then you replace c by x again. So this is just the same as theta, right? So then you get this thing up here is the same as that. Well, using x instead of y, but same thing, right? So it's just kind of rewriting of the same thing, but using just restating it in a slightly different way. But it's going to be more appropriate to what we do. Another corollary is that if, again, c is not a constant symbol now, not in theta or psi, and you can prove that gamma together with theta, where x is replaced by c, can prove psi, then gamma together with the assumption that there exists an x theta can prove psi. And the idea here again is that if theta c, the constant c doesn't occur anywhere, neither in gamma nor in psi nor in the rest of theta, and you can prove that, but this assumption using c is enough to prove theta, that psi that doesn't use c, then actually all you used is that there exists somebody that satisfies theta. It didn't matter that it was c or who, because you didn't use c at all. So if the system works well, this should be the case. again, we are trying to prove that the system works well, so we don't know this should be the case, and we need to prove it formally. Though this follows pretty much from what we have so far. So for this, we need to use this theorem that we proved last week, that's called contraposition, that if gamma together with phi proves not psi, then gamma together with psi proves not phi. That was a typo right there. So not phi. That's what we need right there. So like we are negating both essentially. So you know what a contrapositive is mostly. So if you want to prove phi implies no psi, then you can assume psi and prove non phi. Same thing. So we proved that last time, and that's what we're gonna use here, because so what is the proof? So we know that gamma together with theta xc proves psi. Now by contrapositive, we get gamma together with no psi xc. We're using here, I guess, the fact that not psi is the same as psi. That's because it's a tautology, and therefore they are equivalent, not psi and psi. So applying not twice is the same as nothing, and that's because it's a tautology. It's technical commentary. And then from here, we get now, by the application of our theorem or our previous corollary, that we get a gamma together with not psi proof for every x not theta xc, which then by contrapositive again, we get that gamma together with the negation of for every x not theta proves psi, not psi. And now that's what we have. So this one here, notice that this guy here is exactly that exists x theta, which is what we want. All right, so those are the corollaries that we need. Let's make it just a few more of these meta-theorems observations. One is called alphabetic variance. I'm not going to do the proof for this one, so you can read it in the textbook. It's similar to the other one. It's in the induction or in the length of the deduction, or you just play with the deductions. And it says that suppose that phi and phi prime differ only on the quantifier variables, right? So for instance, suppose one is of the form for every x there exists a y such that something happens, some relation happens of x and y, and the other one says for every v there exists a w such as the vw. They are the same sentence, they mean the same thing, right? So the difference between them is purely syntactical, right? So they should be completely equivalent, and they should kind of imply each other, right? That's what the theorem says. So this is what it should happen, but again, our definition of the formal system is purely syntactical, purely formal, and there is no should in what we have. I mean, should is because it's what we want, but there is no intuition for this yet. Why is this going to be the case? Well, you have to actually prove, you have to do a syntactical proof that you can go from one version to the other, where you are changing the quantified variables, and if one is true, you can make a deduction and get that the other one is true. That requires some little playing with the deductions, generalizations, and it's a bit tricky, but it's not very tricky. And you need it for the applications that we're gonna do. But then it's gonna save you a lot of time, because then if you have the wrong variable, well, you can just flip them for the other variable, the one you want. And that would allow you, for instance, to use the group axiom 2 in some situations where it could be complicated, right? Because here you can use only axiom 2 when t is substitutable for x inside alpha, right? And that meant that no variable that shows up inside t, let's say a y variable that shows up inside t, can become bounded once you do the substitution here, right? Because if maybe you put a y there that the x wasn't bounded, but now you put a variable inside t that becomes bounded, that's gonna create trouble, as we saw in some videos ago. So you can only use t's that are substitutable for x, but then what you can do instead is inside alpha, that variable y that was bounded, you can just change it for another variable that doesn't show up in t. It's a bounded variable, so if you change it everywhere, you don't change anything. So that allows you to do substitution by changing a few variables and get that. Okay, so this is possible. Just change the variables, and if one proves the other. Again, this needs a little deduction. Read in the textbook. Another thing that is important, and it's going to be important for us, is that equality is a congruence relation. Right? Equality symbol. What does it mean, a congruence relation? It means that it's an equivalence relation and that it preserves functions and relations. So what do I mean by that? I mean that we can prove, with no assumptions, with no gamma, we can prove that for every x equals x. So the three axioms that define an equivalence relation. So for every x and for every y, x equals y implies y equals x. And you can prove that for every x, y, and z, if x equals y and y equals z, then x equals z. So proving these three kind of are saying that equality is in an equivalence relation. And then what does it mean that there is a congruence? Well, so first let me say, to prove this, you need to go and use the logic axioms and maybe do a couple manipulations. It's not too hard. It's a good exercise to try. It's a good exercise to try before you read it in the textbook how you do this. They're all very short, these proofs. And congruence means that it preserves the structure in a sense. So if, let's say, R is a, let's say, binary relation, just to simplify. But this, you can do it for an n-ary relation the same way. You can show that for every x and y, if x and x1, you can show that for every x, y, x prime, and y prime, if x equals x prime and y equals y prime, then the relation holds of x and y if and only if it holds of x prime and r prime. So r holds of x, y, if and only if r holds of x prime, y prime. So the relation behaves the same way if you replace things by things that are equal. I mean, this is obvious if you're thinking of the intuition of what these things should mean, but equality is just a symbol for us. It's a symbol that satisfies those axioms, the logical axioms that we put about equality. That's all essentially, like, syntactically, that's all we know about this two-line symbol, equality symbol. So all these things need a formal proof. They are not obvious in any sense. The fact that all these properties just follows from those axiom 5 and 6 up here that are the only ones that use equality and follow from modus ponens. The last thing you need for to get a congruence is that if f is a binary function symbol, and again, that doesn't need to be binary, it can be n-ary, and just using binary to simplify the notation, you get that you can prove out of nothing that for every x, y, x prime, y prime, if x equals x prime and y equals y prime, then f of xy equals f of x prime, y prime. So you can also prove this, and these are the properties of equality that tell you that it's a congruence relation. It's an equivalence relation, and it preserves the functions and the relations. Each of these requires little proof, but they are not hard. You should try them out. Okay, see you next.